In this video, let's see how we can build a concurrent processor in Go. We'll be using channels and wait groups. At the end of the video, I'll show you a trick to write drastically less code without using channels. After writing code for over 20 years and writing Go for over 10, I find the best way to make code concurrent is to start by making it sequential. Then we can improve the performance by making it concurrent. Let's first create a mock item we will process in our pipeline. Now that we have an item, we need to process it. Let's create a simple function to do that. Now we need to populate a slice of items that we'll operate on. And then we can range over those items. And this was added in 122, or we can just specify range and then a number. And we need to create all the items and add them to the slice. Now as we range over all the items in our slice, we're going to call process item for each of them. And you can think of this as processing one item at a time. As each item is processed, it goes to the next item, and then it goes to the next item. But we want to do this concurrently. So if you think about 3 Go routines running, we want to have each of these run at the same time. So instead of just one at a time, we're doing 3 at a time. So let's fix our code to do that. We need to create a channel, and we can insert items into the channel instead of into a slice. So let's insert them directly into the channel. This works, but it only operates on a single item at a time still. We can make each process item call from within a Go routine. So now this creates a Go routine for each item, but it creates a big problem. Let's see what happens when we run this. The program will just run and exit without processing anything. We need a way to wait for all the Go routines to finish. That's where a wait group comes in, and a wait group is part of the sync package. You add a number which is done typically within a loop, but not inside the Go routine. Otherwise, the main program won't wait. Then you need to mark when one of the items is done, and defer works great for this. Now we need to wait. Now let's run it. Each item is now processed in a different Go routine, gives us the performance boost we've been after, but it still has some problems. What if there are a million of items to process? We don't want to launch millions of Go routines at the same time. We can fix this by creating a semaphore. And so a semaphore is just a counter that works across Go routines. Think of it like a turnstile. When we let one in, it controls how many can go through the turnstile and how many are in the middle without letting others in until the ones that are inside are also let out. So when one is let out, the next one can also go through the turnstile. Now Go doesn't have a native semaphore, but we can mimic one using a channel. This semaphore will only allow 5 at a time, so you can see we're creating a structure channel with 5 items for space. When one goes through the turnstile, we add it to it just like any channel. Now we let one out of the semaphore when the Go routine is done. This will allow more to come through the semaphore. And let's add a sleep within the process item so we can see how this is working. When you run this, the first of the 5 goes through and they all sleep for 1 second. The second group of 5 are then processed and then sleep. So we're handling quite a bit in this little block of code. Let's go over those. It's concurrent. It limits the number of workers that we have so we can control how many are operated on at the same time. And it also waits for all the Go routines to be done before exiting. But it does not handle errors. We need to fix that now. So we can create an error that we're going to capture from any of the Go routines. We can capture the error here, but do you see a problem with this statement? It is within a Go routine, so multiple Go routines could write to this value at the same time. We need to protect it so it is only written to once. We can use the sync once for this. However, you could also use a mutex. That also works. Finally, at the end, if there is an error, we can print it. If you're within a function, you would simply just return the error as well. Now our app is getting a little bit bigger. Let's see what it does well and what needs to be improved. Again, it is concurrent, so we can process many items at once. It limits the number of goroutines rather than being unbounded. And then it also waits for all the goroutines to finish. It also handles errors now, where it captures the first error that happens. However, it is not context aware, meaning that one item processor is not aware of another processor that might be failing. They'll all continue to run even if there's an error in one of them. I also feel like this is very hard to read, and we also don't have any business logic in here. This is just for handling the concurrency. So how do we improve upon this? Well, there's a package that handles a good portion of this, and actually what we have here is a very naive implementation of this package, and it's called the errgroup package. So now let's see what we can do to use this package. Let's clean up the code by removing the channel logic and switching back to a slice. Now next, this block here can be reduced to just a single errgroup variable. And we're also passing in the context background, and we'll talk more about this in just a moment. Now this whole block here that handles the semaphore, the wait group, and the error is reduced to just the goroutine and the process item function. In order to use the error group's goroutine, we call the function on the group instead of starting our own goroutine, and it looks like this. We can now simply return the error from the process item function, like this. And finally, we can combine the wait and the error processing into just the error group wait that returns an error at the end of our function. So now let's look at what all this handles now. It handles concurrency. It limits the number of goroutines, and we are waiting for all the goroutines to finish, and we're handling errors, and it's also much more readable in my opinion. But we're still missing is to be able to handle cancellation between the workers. So let's fix that now. Now instead of ignoring the return value, the second return value from the with context, we're going to capture that here as a CTX. And now the process item, we are going to also pass in the context into that function. And now we need to actually update the function signature itself to accept a context. Now within this function, we don't have any business logic, but to show an example of using a context could be such as calling a database such as this, or it could be an HTTP request where if you're passing the context and it's canceled, the actual network request will be canceled as well. The main point here is that if one of the goroutines stops due to an error, it can cancel the others without being blocked. To show an example of this, let's say you have 3 goroutines running and one of them hits an error. You want the others to stop what they're doing so you can return an error from the errored one and the others cancel. Let's review where our application is at now. We have concurrency, limits, waits, errors, and readability, and now we have also solved the context issue. If you have any questions, drop them in the comments. If you like this video, please like and subscribe. Thanks for watching, and I'll see you in the next video.